Suppose that you are given a curve and you would like to find the length of that curve. Applications would include finding the length of a winding road, or maybe finding the length of a road course in a race. How does someone actually find the length of that curve? Well, we want to apply the same ideas that we applied to finding area under the curve and volume. And that is to chop this into pieces. So we could break this curve up by breaking up our interval into pieces. And then along each piece, we can approximate the length of the curve by using straight line segments. Now, of course, this is just an approximation, but if we use more straight line segments that are shorter, then as we continually increase the number of line segments, we should get closer and closer to the true length of the curve. So for example, I could double the number of points, and I could take shorter lengths of the line segments, and then you would get approximations that are much closer to the true length of the curve. And that's going to be our strategy. So we want to formalize this strategy by finding the length of a curve. By considering a function, we'll call that function f of x, or y equals f of x, on the interval from a to b. And we're going to break up the curve into straight line segments, as you can see pictured below. Here we're going to, as usual, let delta x be b minus a over n. That's going to be the x length in between our line segments. Okay? Then we need regularly spaced points. Those are going to be x sub k equals a plus k delta x. And then the y values, or are going to be the f of x values. So what I want to look at is I want to zoom in around here and look at one of those line segments. So if we zoom in, we can actually find the distance between these 2 points. Okay, the way we do that is to use the Pythagorean theorem. So I'm going to draw a triangle, and I'm going to note that this length is going to be the difference in the x's. So it's going to be x sub k minus x sub k minus 1. And this length is going to be the difference in the y's, y sub k minus y sub k minus 1. Okay, and then the hypotenuse I'm going to call d sub k. And we know that from the Pythagorean theorem that this length squared plus this length squared should equal that length squared. So the distance should be a familiar formula. It would be xk minus x sub k minus 1 squared plus yk minus y sub k minus 1 squared. So essentially that's the distance formula, which of course comes from the Pythagorean theorem. So that gives us the length of one of these line segments. Now what we want to do is add up all of these line segments. So we're going to let s sub n be the approximate length of the curve that comes from adding up these line segments. So s sub n is going to be the sum of those lengths. We'll call them d sub k. So it's the sum from k equals 1 to n of the square root of x sub k minus x sub k minus 1 squared plus y sub k minus y sub k minus 1 squared. Now, we're going to call x sub k minus 1 the distance between two x's. We are going to call that delta x. And then the y sub k's, of course, are f of xk. So I'm just going to rewrite this sum for a second. This is going to be delta x squared inside the square root plus f of x sub k minus f of x sub k minus 1 quantity squared. Now I'm going to factor out a delta x from the square root. So what I'm going to do is I'm going to have this square root here, and then I'm going to factor out a delta x, or a square root of delta x squared. So that what's left is going to be 1 plus, and then this will be f of xk minus f of xk minus 1 quantity squared. And then because I factored out a delta x squared, I'm just going to put a delta x there inside the square. So by factoring out of a delta x from the square root, okay, so I'm going to factor out the delta x squared first, and then when I take the square root, that's going to just give me delta x on the outside. So a good question to ask is what does the squared term under the radical look like here? What does this term look like? I see f of x at one point minus f of xk minus 1 over delta x. So in fact, I can think about this as this is f of x sub k minus 1 plus delta x minus f of x sub k minus 1 over delta x. And hopefully that looks like a derivative to you. So in fact, the squared term under the radical looks like an approximation of the derivative, f prime of x. So this is an approximation of the derivative at x sub k minus 1. Now, what kind of sum do we see here? Well, I have an expression in the radical times delta x. And so sums that look like a function times delta x, those are called Riemann sums. Okay, so we have a Riemann sum that's approximating the length of our curve. So how do we improve the estimate? Well, we can increase the number of line segments, capital N. Of course, if we increase the number of line segments, the same thing that happens is that we're going to decrease delta x, because we're remembering that delta x is b minus a over capital N. So you increase n, that decreases the delta x. So in fact, we can take the limit as n goes to infinity, and this Riemann sum that I've put here becomes an integral. What is it an integral of? It's going to be integral of the square root of 1 plus, and then there's going to be something squared dx. What is in the square term? Well, as we said before, what's in the square term is an approximation of f prime of x. And if you look at that approximation and you let delta x go to 0, then that actually becomes the derivative by the definition of the derivative. So that limit as delta x goes to 0 is going to turn that approximation of the derivative into the exact derivative. So this is actually going to be f prime of x, quantity squared. And then, of course, we want to start that integral at a, and we want to go to b. And so little s is called the arc length, okay, which is the length of that curve, and it's given by that integral. Okay, so let's look at an example. Our example is going to be find the length of the curve, the square root of 4 minus x squared. So first of all, I want you to realize that this is actually going to be the equation of a circle. So we have a quarter circle here of radius 2. So we already know that the circumference here, the length, is going to be a quarter of 2 pi times 2. So we know that the answer is supposed to be pi. Okay, but what I would like to do is to use our technique to show that this is going to be pi. So the first thing I'm going to want to do is I'm going to want to, for my function, which is the square root, it's going to be 4 minus x squared to the 1/2 power. I want to take the derivative. And that derivative is going to be 1/2 times 4 minus x squared to the negative 1/2 times the derivative of the inside, which is a negative 2x. So the derivative is in fact negative x over the square root of 4 minus x squared when I simplify. Notice that the 2's are going to cancel there. Okay, so s, which is my arc length, is going to be the integral from 0 to 2 of the square root of 1 plus the derivative, negative x over square root of 4 minus x squared, dx. So we can write that as the integral from 0 to 2 of the square root of 1 plus x squared over 4 minus x squared dx. Now that integral does not look simple at the moment. Let's see if we can make some simplifications. So I'm going to add these two as fractions first. So I'm going to take the square root of 4 minus x squared over 4 minus x squared plus x squared over 4 minus x squared. That way, when I add them together, these x squareds are going to cancel. And I'm going to be left with the integral from 0 to 2 of the square root of 4 over 4 minus x squared. Now I'm going to rewrite this by multiplying the top and the bottom of this fraction by 1/4. If I do that, then I'm going to get the integral from 0 to 2, the square root of 1 over 1 minus x squared over 4 dx. Okay, it's not immediately clear what's next, but I'm going to let u be x over 2, and then du is going to be dx over 2, or dx is going to equal 2 du, so that this becomes 2 times the integral from 0. Now x over 2 is 0 over 2, but when I let x equals 2, then u is going to be 2 over 2, or 1. So it's the integral of 0 to 1, 1 over the square root of, because I can take the square root of the top and the bottom, so this is 1 over square root of 1 minus u squared du. And that is something I do know the antiderivative of. So this is 2 times the arc sine of u minus, sorry, not of u. Yeah, 2 times the arc sine of u evaluated from 0 to 1. So that's going to be 2 times the arc sine of 1 minus 2 times the arc sine of 0, which is 0. And so finally, I'm going to get 2 times the arc sine of 1. Well, the sine of pi over 2 is 1. So this is 2 times pi over 2, or pi. So we got the answer that we thought we were going to get, that the length of that quarter circle is pi. Now, you may say to yourself, why did I do that example when I already know that length? And the reason that I did this example is that this formula for arc length is quite complicated, as you saw. And only in very rare circumstances will I be able to substitute in for the derivative right there and get an expression that I can integrate algebraically. In most cases, I'm going to get an integral that I don't know how to solve. And so in most cases, when computing arc length, you're going to have to do a numerical approximation of the integral. So essentially, in most cases, you're going to be chopping up this curve into line segments and then summing up the line segments. Okay, we might use more sophisticated techniques by doing things like the midpoint rule, the trapezoid rule, or Simpson's rule to estimate this integral. But essentially, that is equivalent to chopping up my interval into pieces and then summing up those line segments.